Okay, so I still need to remind you, we will have midterm exam to be held 25th of October. That means next Tuesday. So that is again, most likely you need to prepare for this kind of exam. And also if you look at this kind of grading, and then so the TA has grade the homework number 1 and number 2, so that I just want to remind you that you need to really study for this exam. Okay, of course, I will give you some quick discussion about this kind of homework. I noticed some students have done a good job, but still some students didn't spend enough time for this homework. So let me quickly try to describe about this homework for some of you now who again, I still remind you so that we really want you to spend time to study and to understand this kind of concept of this kind of vibration engineering, so that if we just simply try to we can tell, either the TA or me, I can tell if you spend time to do homework by yourself. If you really try to copy your classmates, TA or something, say then I will look at that your homework again, and then do some proper deduction of your score. I need to give you all the warning. If you don't do the homework by yourself, I will try to double check about your homework again. There's evidence. If there's clear that you copy your classmates this kind of homework, I will give you 0 mark in the grading, so that the TA already seen, but it's clear. Some of you, if you don't follow this kind of our UST policy, I will try to make additional deduction. So that is something I need to let you know. You submit it, then I do want you spend time to do homework by yourself. I have to let all you know, okay? And so for the first one, and it's simple, but I also remind you that if you just simply try to show this one without simple explanation why you get this one, then you need to be careful, right? That's something why you try to propose this kind of the model for this model for this chapter. If you simply show this figure without any explanation, I will try to follow up. TA, I'll give the preliminary grading, but something I have provide you additional reference on our Canvas website, so that if you don't really try to say, then anyway, I'll just tell you why. So for this particular song, I already mentioned in previous lecture, and our Canvas, our additional information, so that try to let you understand about this kind of real frequent response function or vibration or response of this kind of the car or something car model. Okay, and this one, I think this is not challenging, but I also let you know that the problem I ask you to do is some of this is related to some real vibration engineering in field study, so that it's important for all of you to have some understanding about the real vibration engineering. That's something I emphasize many times right in the beginning, so that I don't want you to simply, you do homework and then, so without understand this kind of engineering aspect of this kind of the work doing that. I still need to, of course, that's why I also provide you, so you do the homework, and then the things, if this homework relate to real vibration engineering, So that, for example, this company, they do have this kind of product, right? For our local this kind of engineer to use in vibration engineering, so that so that I tell you. And then number 4 is that's another thing I also mentioned, so that and this also is not just basic homework, but in reality, so that many vibration passive vibration control will involve this kind of nonlinear component, right? You have MCK, and most likely sometimes your vibration isolator and vibration damper as somehow is nonlinear, and then so that here it's just tell you that you see, and then of course I would mention several products I show you is most likely they're nonlinear, so that this kind of thing is give you some real understanding about how we engineer can really use simplified, linearize the model, right, to work on vibration engineering. Okay, so that here give you some of this kind of real. You see, typically it's nonlinear, so that how you can try to get some reasonable good estimation about this kind of equivalent, the spin constant, or equivalent this kind of MCK or something for vibration engineering. These are something important for all of you to understand. Okay, and then of course this is an open-end question. Again, I noticed some of you just simply copy some content from internet without some additional discussion or something, and then so that again you already submit this one. I will again look at your solution again and try to do some additional minor like modification about the grading result, so that so this is something important. I do want you to really carefully, right, spend some time to look at how you can learn some practical this kind of knowledge skill in this area. Do you have any question? Again, all this will be including most likely the concept in the lecture note, and homework will be included in probably something in the midterm exam next week. And then the second homework is of course one student last week asked about some question for this kind of mechanical property, right? So that at least I already give you some basic advice, right? So that many of this kind of practical vibration engineering, most likely they don't have well-defined parameter. You need to look in some handbook, mechanical engineering handbook, or something to decide something, so that I think this is something is important for all of you to understand. In practical engineering, you need to dig out some of missing information. For this part, of course, basically, if you use Newton's law, and then you can derive this kind of equation motion for one defeated MCK model, right? But this is a torsional system, and then under harmonic excitation, then you can try to, again, using our sound mechanics, right, to determine equivalent spin constant. Again, I already remind you that you can look at things. At least some student ask question, I give you something you right. So some practical engineering, you may want to look at some handbook, right? For typical mechanical property to determine this kind of spin constant. So that typically for our UG sound mechanics, I do think you should have basic understanding, right, about those typical Young's modules and the shear modules. And then, of course, again, this gives you some ideas that you need to think about things, right? And of course, I also provide you some information, right? Once you do the homework, and then next question is how big the vibration is good or bad, so that for this kind of propeller, this kind of vibration, they do have industrial standard, right? Industrial standard, and so for example, I show you one of propeller vibration standard from US FAA, so that this well-defined vibration, this kind of output, so that I just tell you that you need to, as I mentioned, right, for different industry and a different kind of requirement, right? So that for marine engineering, for aerospace engineering, the different industry have different standard. So because this is from US the government, so that the standard they specify is, you can see, inch per second, but you can easily convert into our standard unit. And finally, another one is a precision grinding machine. So that this is also not challenging, but it's also important for all of you to understand this kind of thing. You can look at the frame response function, while we discuss in our lecture, and then to determine. Of course, you can also use this kind of Excel program. Then you try to enter those given conditions, and then try to determine this kind of input-output response, right? And then calculate the output, right, in terms of vibration amplitude. And this one, number 4, is another, I think it's something we also mentioned, right, in our previous lecture, so that it's not challenging, but at least this is a force-induced vibration, okay? And finally, this problem is a little more difficult, but I to tell you that if you look carefully, and then still you can do this thing, right? So that if you can do some simplified model, we mentioned this one, and then based on Newton's law, you can derive equation of motion. Under harmonic vibration, you can try to analyze this thing, and then eventually you can calculate this kind of the frequency, natural frequency, right? And then actually this can has exact solution actually, and then it's a quadratic equation for omega square, right? And then determine this kind of critical velocity. Okay, anyway, I just tell you, this is give you. Do you have any question? I just make sure that you understand this is something I really provide some you additional information. Okay. Of course, I also last time is found out about how we discussed about mechanical vibration of whole body, right? So that will describe human body can be constructed in terms of a multiple MCK model. So that then the question is many of these kind of product, VR, AR, MR, metaverse, they're going to have a lot more this kind of sensor, right? And then how to create using all these sensors to create this avatar human body dynamic model, right? So that this is something quite important, big business. How big is the business? What do you think? Are you able to make this kind of sophisticated human body dynamic model as avatar? How many degrees? We also ask you this question. So that what do you think? Of course, following about this avatar, right? You have using some kind of sensor including some motion sensor, checking about human body dynamics, or simple image sensor, or LiDAR, right? In iPhone 10 or beyond, with LiDAR, using this kind of solid state laser, VCell, right? And then try to do this kind of thing, right? So that in this case, if we have this kind of sensor, human, to capture human body dynamics, capture this kind of human facial recognition, and then can recreate the model, right? And make your own avatar. So these are something I would say quite important, interesting. This is another big potential business, right? So that I just show you another quite interesting. There's some stock company in Los Angeles. Okay, do you have any question? Huh? The question, please, I don't want you to, we have a limit time in our lecture, so that the question, please, now raise your question. And so that, yeah? You post the answer of the slide. Actually, it's already on our, it's already on our homework. I will give you here, if you try to look here, we have solution. But okay, I should give you a PDF version, the solution, full solution here. Okay. Anyway, so I tell you that this kind of how human body dynamics, and it's another big branch of news concept. Right? If you can make a very good digital human body, for digital human, so that it's another huge business, right? With AI, and then so that this is something not small. It's I would say big business, right? So this guy Akash get the $150 million for his this kind of interesting genie, 3D avatar, NFT wearable. Huh? What do you think? Can you make this kind of human body model better than this genie? What do you think? That's something worthwhile for you to think about. Huh? What do you think? So what do you think? If possible, you can make even better human body dynamics model. Huh? It's somehow it's not make it fun.
Genies have a twist. The emojis react to what is going on in real time.
My name is Akash Nigam. I'm 27 years old. I'm the CEO of Genies, and this is my hustle.
What do you think? Huh?
Well, our goal as a whole is to create the next human race.
Genies is a 3D avatar that looks and thinks just like you.
Genies are unique in the sense that they're, again, 3D, they're animated. We come out with different actions, right? So different like packs every single week based on whatever's relevant happening in the world.
Genies is available on Instagram, WhatsApp, Messenger, iMessage, email, Slack, pretty much any platform that you want.
We want every single person on Earth to be able to have a genie, a digital representation of themselves.
Digital human,
our
but
art style is very different. Like, we like to call it like 2.9D. It's like kind of as close to 3D as you can get on a 2D character rig.
You know, we've built out AI technology with even the way that the genies are animated and how you can express yourself through the genie.
So we have a patented composer process where we have these innovative wheels, as we refer to them.
Literally spinning the wheels in real time, your genie's moving and changing and reacting to kind of how you're changing the nose, how you're putting on the shirt. There's thousands of different assets essentially for you to choose from.
And that's why the wheels are so fun, just because they offer so much variety and different creative expression. The Avatar Agency is one aspect of the company where we represent over 300 different talent, and we pair them up with brands.
We really started working with kind of the top names around every industry, and really what that entailed is we create them a fully custom genie avatar and then let them use it for anything that they want.
So when someone like J-Lo comes to us and, you know, she wants to do an entire music video that might be 3 minutes long, we typically can turn that around within a few hours.
Celebrities all use their genie in different ways. Pink and Khalid used their genie in a lyric video. Robinson Cano, he hit a solo home run. He replicated that in genie form. He shared it on his social that next day. Offset, he was doing an Instagram takeover for Vogue. In a few hours, we turned around his genie walking down the Vogue runway. He was able to put that on his social, fulfill that brand partnership. Vogue was extremely happy because the engagement on it actually outperformed Offset's physical self doing something similar.
Gucci's obviously one of our main partners. So right now, if you go through the app, you can adorn yourself in all different types of Gucci clothing. They paid for exclusivity over that sector. Bird contacted Becker maybe a few hours before their big announcement of the year, when they want to again activate around 20 different influencers ranging from Dylan Francis, Lil Nas, Billy Ray Cyrus, Manny Machado. It's just like a large a large variety. Because we had already pre-designed a bird scooter and we already had all of those genies already made, by morning time, we already had a massive campaign flowing on Instagram, which again, in the real world, that would have taken months and months and millions of dollars. For us, we were able to do it on pennies on the dollar and then flip it on an hour's notice. So next 2-3 weeks, very important, same type of tempo as during launch.
Just give you some.
Went to University of Michigan, studied computer science, kept trying to come out with different apps with Jake and Evan. Most of them were just.
Well, I tell you why, so that we are in this kind of new world. So that if you really have learned a lot more beyond what this course, and then it can be interesting, right? Thing to make this kind of avatar and so in the virtual world, right? In the metaverse, that something is again, this kind of potential is not traditional engineering, right? If you work as a maintenance engineer for building service industry, how much you can make, right? 1 month, maybe I would say maybe $20,000, $100, but if you make interesting this kind of thing, then potentially this kind of avatar, 3D avatar can be interesting. And I think this thing in the virtual world, because I believe a lot of you try to use smartphone app all the time, and so that you are connect to the virtual world, the Facebook or the social media. So that that's why this kind of Facebook CEO and all this kind of big company, they try to create something VR, AR, MR, metaverse, right? So that this kind of virtual world has potential big business. What do you say? Huh? Did you have any idea how to make this kind of avatar for your avatar? Maybe can another homework. Huh? Can you make your own avatar? Huh? What do you think? Is that difficult or not easy? Easier. Start from those kind of course, definitely is you need to think about how many degree freedom, right? We have n degree freedom to categorize this kind of digital human. Why? How many degree freedom would be necessary to show interesting this kind of virtual human, digital human? Huh? What do you think? How many degree freedom? Huh? It really depends. I would say it depends on you define, right? You want to have a minimum. Of course, all engineers will want the minimum degree freedom to have some good this kind of good looking, this kind of digital human. So that so this it can be simple, but of course that's important question, because you have too many degree freedom. What happens? It's too complicated. It spend a lot of time to build a very complex model for simulation for this thing. So it's something quite important for you to think about this thing. Of course, nowadays, you see, those kind of your smartphone, like iPhone, can quickly make the sound avatar actually using this kind of a built-in sensor in smartphone. Why is that? So how they do it without spending a lot of time to build your own model, right? Human body dynamic model from scratch. Is any way you can try to create this kind of avatar, your own avatar, now using existing this kind of software in a smartphone app, even some of this kind of iPhone or some of special built-in function of your smartphone, right? So this is something from my point of view is important, interesting. If you make a good NFT wearable for the avatar, it can also make money doing that. Okay, anyway, so it's something interesting for all of you to think about this thing, right? Beyond what we described. Okay. Anyway, so do you have any question? If not, then I think we just, this is again, it's additional information. From my point of view, I think it's at least I hope you can pick up some of this kind of interesting thing for you, right? So that that's why I already emphasized, right? So I do hope you can learn something interesting and useful, right? Interesting and useful It's not something you do the homework and have exam something. Yeah. Okay, so that I think we need to go back to our lecture. Do you have any question? Any question you have about what we just described in the homework and thing? Anyway, we already try to describe about this kind of MCK model for vibration engineering. So this part, I think we don't need to think. Of course, emphasize about the engineering application, right? So that for different engineering application, different standard, like ISO standard we mentioned for human body dynamics, right? So different this kind of motion variable, right? Observation affect the human comfort, right? So that's some, and rotating machinery is also important. We also give you homework, right? And also we also mentioned about simplify the vibration thing. And last time we also mentioned about another important issue about cell excitation thing, right? So definitely is a quite important branch of vibration engineering. So that the key problem of this thing again is what? Many times for some mechanical system, what's the problem? Your MCK mass spring system, this model may depend on this kind of external condition, flow condition, right? We mentioned in the first lecture. So that in this case, cell excitation, that means some parameter in MCK, most likely maybe C, damping function of input parameter, input velocity or something. In this case, if input velocity too big, and then you can cause some flow-induced vibrations. This is what we just mentioned, right? And then, of course, this involves many engineering problems. In the homework, will tell you about this kind of antenna in the car. And also we have what? Flow-induced vibration in the pipe for HVAC or some building engineering. Right? We also tell you about this tuning. Basically, this is something quite important, right? I think once you have certain flow-induced vibration, and then so that can you create some simplified model, right? One to feed the MCK model, or this particular one is related to the vibration of continuous medium, cantilever beam, right? So that in this case, cantilever beam has an infinite degree of feeder, right? And then so that based on what you learn in solid mechanics, mentioned, so that you have Wx and T, right? The diffraction curve W. And then so that based on, we'll describe this one, right? Based on seeing then the natural frequency of the first fundamental probe can be related to square root of EI. EI is bending stiffness you learn in our solid mechanics. And beta 1L is a constant, okay? So in this case, it's very easy now for you to think about how we can analyze this kind of problem, because we know this kind of all the mechanical property and geometry of this particular mechanical structure, and then we can determine the natural frequency, right? And then next one is based on, we mentioned Joule number. This is a constant for certain object. If you have this kind of cylinder structure, and then so that then the Joule number is constant. So in this case, we can easily determine this kind of velocity, critical velocity, to induce this kind of flow-induced vibration based on our natural frequency and geometry, diameter of this kind of a cylinder. So this is something I think is important for all of you to have some basic understanding, right? So it's not too difficult, but the key thing here is Joule number somehow depends on what? Geometry. So that for 0.01 is only for what? For this cylinder, Why? Diameter of D. But if you have certain maybe object, it's not only cylinder. If you have like building, what happens? If you're building like this one, and what do you think? What's the structural number? Tall building. Why? This one is related to the cylinder. And the Joule number will maybe will be a little bit slight difference. So that I told this definitely this is a C, and this kind of maybe building, so that I tell you that of course that's a difficulty. Okay, so that but in general, we can try to, if you don't have enough the time to study all this very complicated flow-induced vibration problem, and you use this as a preliminary way to determine this kind of flow-induced vibration. Okay, that's something I tell you. Of course, I can give you additional reference, right, about more complicated structure and what's corresponding Joule number. And then, of course, last time we also mentioned about that's another thing, right? So that if you see, if you have not only simple MCK, C is not a traditional viscous damping, but is related to, for example, the dry friction or the Coulomb damping. In this case, based on what we learned in our engineering dynamics, how can we do? Basically, is we can analyze our summation of the force into MA, right? So that we have actually two forces. One is spring force, another one, dry friction. So that this one is what? What's the difficulty of this dry friction force? What's the problem? What's the problem? What's the problem of this kind of vibration? What's the problem? Compare with our previous simplified model, MCK. It's nonlinear and much more complicated, because again, it depends on, you can see depends on the motion, right? Velocity. You see here, I show you this. You see, if you here velocity negative, velocity positive, and then your result, the sign of this force will be different. So that compare with our MCK model, right? And mass spring viscous damping, and then so that this give you much more complicated way to describe this thing, right? Of course, we can use MATLAB to describe this kind of a very complicated force, and then this force what emphasize this kind of F dry friction is what? Function of what? Function of velocity, right? Velocity, let me X. And it's a nonlinear function X dot. Okay, this is something will make this thing, and then so that that's why this is something is more complicated for us to analyze. Of course, we still can analyze this problem, but what? Make assumption, right? If in some condition, our velocity of this mass is positive velocity, and then we can analyze this kind of a response to that, and then if so that we still can analyze, but if we need to do some more complicated analysis, right? Another approach is we may want to look at from energy point of view, if we have do this kind of harmonic vibration for this kind of mass spring system with a Coulomb damping, and then look at we have a go through harmonic vibration, right? This force, and then we look at response X, and then to see what happened two things. And then in one cycle of this harmonic vibration, and then we calculate total energy dissipation. And then in this case, we may want to get the equivalent damping coefficient, right, for this kind of dry friction, so that in this case will be easier to do analysis. So this is something mentioned. Once you have very complicated nonlinear behavior, sometimes engineer we want to make our life easier, right? Get the equivalent this damping, viscous damping. And of course, if do this thing, then we can try to use the frame rebounding we learned in previous part, right? For our MCK and C is viscous damping, right? So that this is give you a way, right, to simplify this nonlinear like a mechanical system with this kind of a dry friction. And then so that anyway, so this is something quite important. And then so that and of course, if you look at carefully about this thing, then so that we can try to carefully understand about this kind of thing, right? You see, for this vibration amplitude and Y is energy dissipation in, and then you see, so that input here, and then we can calculate this kind of energy dissipation in one cycle for mu nx. Yeah. Okay, so that here, of course, we should do some, give you this kind of example how we solve this problem, right? For this MCK, but the damping is Coulomb damping and dry friction. So that if this mass is 10 kilogram and a spring constant 4,000 Newton per meter, and the friction coefficient 0.12, and if you have input harmonic force is frequency 2 Hertz, and then the mass vibration with this thing, so that can we try to do this kind of find the amplitude harmonic force applied to mass. So how can we analyze this thing? Basically, this tell you what? It tell you about our output, and then what is our force input. This is the problem we need to design to analyze. So of course, we already, if you try to simplify the equivalent MCK, right, and then it will be easier, right? Basically, we already showing if I can try M, C equivalent, and K, then in this case will be easier. Is that? Well, we try to use this kind of simplified way to analyze this kind of thing. Then it's much easier. For example, here our M is 10K, K 4,000, and our frequency, driving frequency. Right, of course, this one is what, 2 pi f. F here is 2 Hertz. And then so that the amplitude, output amplitude, so that if you can, how can we do that? Basically, we can try to think about use what we have discussed in previous slide. See, this is a solution. Why? We can use this kind of simplified model or this one. Why? And we have all the M mass spring constant, and then also here, right? So that we can try to do this kind of analysis. Is that based on here, we can first calculate our natural frequency, right, and frequency ratio, and then in this case, we know the output, but we don't know the input, right? So that's something we can easily use this one to do this kind of analysis eventually, so that determine this unknown the force, right, amplitude of the input force. Okay, so this is one example, but of course, I'll ask you, do you have any other way to analyze, solve this problem? Any other way? Huh? Oh, this is important, right? I will tell you a different way to solve the problem, so that this is only one solution. Can you think about different solution? Huh? The one we show here is analytic solution. The difference is doing approximation. Oh, of course, that is also, I would say, it's possible, but it would be a little more complicated. I know that there's another approach. If you try to look at those kind of, or you use MATLAB to calculate that thing, and then with MATLAB, you basically you can describe this kind of MCK, right? And then describe things so that that's also possible. I think I do have the MATLAB model. I think the student remind you. I can give you, you first describe this kind of M, mass, spring, and friction in terms of functional form, right? And then you need to basically you need to think about how to describe this your equation motion in MATLAB functional form, right? And then you using the this ODE solver in MATLAB to calculate these things. So this is another approach. Basically, I think I do have 100%. I do have this kind of example. Let me see if I can show you that example. Once you define that kind of I do have many examples. Here I already show you. Basically, you can define our equation motion in terms of this FEBS, right? And then give initial conditioning, and then solve this kind of ODE using ODE solver, and then plot this response, right? So that of course, if for this problem, if we don't know the force, and then we may do what? Actually, do a series of simulation now. And then until we try to think which this kind of MATLAB, this kind of model can be matched this kind of our given this kind of output. So that basically it's something I told you this something you can try to. Of course, the key thing here is how can we describe our mass spring system MCK in MATLAB. How? Huh? This is another important thing. Let me show you FEBS. Actually, so here, this is our equation of motion. We try to describe in MATLAB. Well, basically it's x dot. So x dot equals certain function, and then the function depends on input time and x. S can be a scalar or vectors, and in case, and then if you give this n, k, and mu, right? Mu is, and then you can see we can describe our x dot. as 2 by 1 vectors, and x dot 1, I mean, first component of thing is 2, x2. And then actually this is, you see, we can describe this kind s dot 2 equals minus mu g sine s2. And then here, this is exactly what we described in our lecture note. Basically, this tells you we define a vector. S1, S2. Right, and then so that in this case, S1 is X2, and then X2 dot. Do you understand? So I just tell you this thing, and then X2 dot is what? X2 dot means X1 double dot. Right, and then equals what? Minus mu g and sine. Oh, this is a built-in function in the MATLAB. And x2 and minus this k over m x1. This is it. Basically, this is the one we describe in our lecture note here. If you look at carefully, and then you see about that. If you look at our actually we just described this equation motion in terms of MATLAB. Do you understand? And then so that I hope you understand about how we can now use MATLAB to describe this in this form. Do you have any question? Any question for this? Huh? Do you understand? Any question? Of course, the key issue now is our for this thing, our Fy force amplitude is unknown. So in this case, you may need to think about, can we do a parametric study? Why? We have certain equation motion described in MATLAB function, m function, right? And then we need to try a series of force amplitude. Is that we try different kind of force amplitude here, and then different F. Maybe start from certain thing, right? From 0.1, and then gradually adjust, and then to see what's our output. Our output, right? Our output this vibration amplitude for different kind of input force, and then eventually we try to find one particular force who can meet our requirement in this homework. So this is I would say you can use MATLAB to do calculation, but sometimes it's something you do parametric simulation to get this result. Okay, I don't know. Do you have any question for I just explained you about how we can use MATLAB to do this kind of simulation? Oh, maybe I think would be better. Do you have any question? I should try to show you. Do you have any question for this? This again, this is a second solution. Let me show you the MATLAB. Okay, let me show you the MATLAB, and then I think it's still important for me to show you about this how we can use this kind of MATLAB, because MATLAB can help you to do even more sophisticated this problem. Okay, so that let me try to open this particular. Here we have this. Right, so that basically this I try to open this kind of M function in MATLAB editor, right? And then of course, as I show you, we can really try to do this kind of calculation. Should I create a series of this kind of MATLAB code? I forgot and which one I should, let me see. Chapter 4, okay. So basically we will try to run this kind of chapter 4 file aperture, this one. So if you key in this one, okay. So we will try to, let me try to show you about this example. Here. Okay, I copy this code. So you see, I define initial condition and use MATLAB ODE 45 to solve this equation motion. Busy now is calculate. It takes some time because again, this nonlinear. Remember, this is it's not the MCK. The C is fixed damping. Take a little bit time. Busy. There be a calculate one. So let me try to I think you have finished calculation. Oh, you see, using this ODE solver, ODE 45, Roche CUDA edit solver, right? We define our MCK, mass spring system with this kind of dry friction force, Coulomb damping, right? And then I can quick calculate this kind of thing. Time, output the vibration amplitude, the two, once as a displacement velocity. See? So this is the result. I tried. Let me see. Did you see the? I think compared with viscous damping, did you see the unique difference? Huh? After certain initial condition, and then when we reach some critical time, what happened? You see, eventually there are no oscillation. You stay, you see, so that this is a very different. If you have MCK or viscous damping, and this is viscous damping, and then you continue have a right. If V is viscous, right, then you have a vibration all the time. You continue to have vibration, and then blah, 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 is that. So these are very different. Of course, the question is how you use MATLAB to solve the same problem we use analytically. How? Huh? How? Basically, it's you need to a series of this simulation. Yeah, a series simulation, right? So that so in this particular example, what's our F? We already find that the force amplitude in this function. Do you understand? So that in this case, it may not be here. Uh-oh. Oh, sorry. This is not. This is a program I create for what? Kaplan-Meier can plot for. I have a microfluidic research project about cancer research. This is another project. Sorry, I should not give you this. I don't know why I opened this. I used MATLAB for 30 years. Huh? I just tell you this is a. Hey, I don't know. I should open this. Okay. Here FEPS. So here we will assume our force amplitude is given. Do you understand? It's given then, but in reality, if you want to do it, and then we may need to try to think about how we change that the force, right? So do you see? So that in this case, this is something I tell you that it's takes some time for you to do adjustment, right? With different this kind of force amplitude, and then how can we do this kind of simulation? Do a series of simulation so that we can really find the right solution. I tell you that is a very different approach. We solve the problem. Huh? I don't know. Do you have any question for the one? Of course, maybe I will try to write a bit more. Basically, now in this MATLAB code, we just show you only one particular case. Is that in this MATLAB code, we just take I give you all these things. Mu is given, K and then the force given is given, and I can calculate our response. X is output. But for this particular example, that means you need to do a series of simulation, right? Series simulation, and then eventually try to find now the one force amplitude can reach this kind of vibration output. That is the real thing you need to think about how to do this kind of thing. Okay. Okay, do you have any question? No question means I hope that this will be in fact in our midterm exam. Okay, so that this is important for you to make sure you have no problem. And then finally, there's another branch. If MCK, and then our damping is what? Material damping. Material damping, that means I show you what we have this kind of a polymer. Polymer using in, for example, that bus, right? The German big company, they try to make this kind of viscous damper for car, so that in this case, we describe that kind of a damping in terms of another way, right? So that this is beta K omega. So how can we see? Again, we also try to use a simplified approach to basically equivalent MCK viscous damping for solve this kind of hysteresis damping, because it also more complicated, right? so that we prefer to see how can we try to create this kind of a simplified way, right? For this kind of a material damping, hysteretic damping, so that in this case, again, we as mentioned that we try to describe this beta, right? The beta is something related to that the parameter for this kind of hysteretic damping, okay? And of course, you can also use complex number approach to describe this kind of thing, right? So that one is here, is related to the traditional spring constant, and this additional term here relate to this kind of damping term. Okay, so this is another way we can calculate this kind of to show a complex number to do this kind of analysis of this kind of M, C, K, and the K, C, right? It's material damping. And of course, for this one, and then if you try to see, then this show you we can for different beta related to material damping, and then so the response will be different. Okay. And of course, finally here I show you this is another important thing we mentioned several times, right? So that for this actually is the ISO Industrial Internet Standard 2631 for whole body vibration. So the X is the frequency, Y is the root mean square acceleration. Root mean square, so that means acceleration from time, right? And then how can we root mean square doing that? So that you basically you try to look here and then here, get some average is kind of a root mean square result, and then so that and then this one is a family of what? The boundary. This is maximum allowable acceleration for certain period of time. If you this vibration is too big, and then human can what? Have only very short period of time to see if you vibration is small, and then human can tolerate a longer period of time. But this gives you some idea, in general. And this can be used for some practical engineering design for example, automotive industry. So basically, here we show you there's actually 3 types of exposure limit for this thing. First is reduce comfort boundary. Second is fatigue decrease proficiency boundary. Different this kind of standard has different application, right? Number 1 for airplane, boat, and tram. Number 2 for flying, driving, and heavy vehicle. And then number 3, exposure limit. Okay, so that this is something I would say important for some of you if you design some kind of automation system for human body, or sit on that car or something, and then this is the important thing. And then for fatigue decrease proficiency, then basically the way things exposure limit multiply and this kind of acceleration divided by 2 over 6 dB. So this will give you something, of course, what we show in curve, right? And then you adjust this kind of thing, then this will give you see. So, and then reduce comfort boundary is divided this thing by 10 dB. So that I tell you that it's only one this kind of standard, right? Root mean acceleration and function of frequency, and then by change this kind of y-axis by certain this kind of factor, then you can use for the three kind of application for vibration engineering. Okay. And of course, actually I show you additional reference on this thing. And they also specify lateral vibration requirement. Is that lateral? That means here, and then a different kind of boundary curve, right? Okay. And finally here, I already mentioned this one, so that the human body can be regarded as what? Multiple MCK model, right? So you have for each component in your human body, a certain kind of MCK, right? And certain kind of frequency, right? So this is something I told you, right? If you want to create this kind of a complete, good human body dynamic and avatar in computer, and then you may need to at least think about how many degree feeder will be necessary to build this kind of human body dynamic or avatar. Whereas now we use this kind of different language, avatar. Yeah. And what do you think? The question is, can you create this kind of avatar? Huh? What do you think? It's important to ask yourself, can you make this kind of this kind of model, human body model, huh? Or we call avatar in computer, huh? And can you also use MECH to simulate kind of human body dynamic animation, huh? Actually, MECH it's not only used for you to look at what we described, right? MECH can create some animation. I will show you some example how we use this kind of MECH to do animation. Things that I told you, MECH do have a very useful this kind of function, and so that I will give you some example how we can make interesting animation using MECH and create some like a video output. Things that let me show you that actually I do have animation simulation. Basically, MECH is very powerful. I'll show you that there's a series of way I can, let me show you. I think I do have a series of a MECH code for animation here. Is that basically once you create this kind of MCK model, what you need to do is undefeated, and then how can you use MECH to simulate this kind of vibration, a function of time, and things. So this is something. Let me show you. Okay, so that basically you solve this kind of build MCK model, and then for example double pendulum, right? And then you can solve this kind of equation motion and using this ODE solver and find this kind of time response, and then eventually you can plot this kind of result, and then let me show you. MECH do have that spatial function, and then show this animation. You see, animated output, MOV, movie. They actually can, once you have a series of like different time, different like which kind of displacement and thing, and then you can use this kind of MECH to generate this kind of movie. Okay. And then of course the question for you is, can you really try to think about let me see. Okay, so let me see. See, this is the power. It can really interesting to, let me show you again. If you solve this kind of MCK, right? And then you can only plot vibration amplitude function time, velocity observation, and then you can just show this kind of how they move. Of course, if you create some human body dynamics, you can look at all the human move around in MATLAB as well. Like you can make a simple avatar to build this kind of animation in MATLAB. I think there's some little error. Sorry, I think I guess this is some actually they can also now show the animation in the MATLAB. Generate some video file. Probably this is something I should modify that code. You see when they try to create output files, there's something wrong. Okay, anyway, I will try to do some modification and a model. Let me show you again. I think the student is don't. Double pendulum. Do you any question for this example? Again, I told you MATLAB is very powerful. It can be useful to solve many interesting problems. Okay. Of course, the question is, can you make this kind of avatar human body do the simulation? What is it? And of course, another practical important thing is, for example, you are engineer design a car, automatic infantry, and then so that then the question is how you evaluate, right? If a driver in a car and then look at the vibration response, right? When you sit in different kind of seat, different design, different MCK, and different response. So suspension seat, standard driver seat, contour a chair. So different design of the then your different vibration response. So then you need to evaluate based on the industrial standard, ISO standard, to make some important decision, right? To see what kind of design will be useful. This is transmissibility. Remember, we calculate input-output response transmissibility, right? XY as function of this kind of damping ratio and the R. Right? So this is transmissibility. Okay, do you have any question? I hope that it's important. You are not only listen to our lecture, you need to study and ask questions. If you don't ask questions and then don't spend time, and then you may not learn the real this knowledge and skill. Again, so that if we have human has a lot of this kind of vibration, and then what happens? Whole body vibration can cause some disease. For those taxi driver, if you stay in the car for a long time, so that it can have some problem, lower back pain, blurred vision, insomnia, headache. So the series of health problems induced, so that in this case, it's important now for many engineers design some machine, right? Some car automation system. Then you need to think about how this kind of vibration of the machine, car, robotic system affect a human body health. So this is something also affect about human people's mover, elevator, escalator, and lift. So this is something important. And there's another. As mentioned, right, for vibration of car, car has very complicated rich body dynamics. So that if you look at wheel, if wheel is not ideal, and then certain kind of this thing, right? So under certain frequency, and then so the certain kind of wheel shimmy instability, especially you don't have do some proper balancing, and then this can be some big problem for car, also vibration. And finally, I show you another vibration engineering for the power transmission line in seeing why the stock bridge vibration damper is used for that I mentioned, right, galloping of this kind of a wide power transmission cable. I think I will show you this one, right? Basically, this is another aspect as I show you that many times we have a complicated vibration problem.
Greetings, this is footage from Wednesday, November 12th at approximately 4 p.m. That is the WXW tower, and we're going to show an example of what galloping guy wires look like. This is the WXW tower, which looks very solid despite a pretty steady breeze out of the northwest, which is prime conditions. We also have light icing, and you're going to see the photographer pan over right now and take a shot of the WHLA tower, which you can see in the distance, and you can kind of see their guy wires galloping pretty severely. Our snubbers just got installed the day before. There's a shot of them attaching to the northwest guy. The wires themselves tied down almost near the parking lot. A little bit closer look. Like I said, just installed, and you see a little bit of movement, but the snubbers appear to be doing their jobs. There's a shot of the guy anchor at WHLA, and there's a little bit wider shot. As you can see, pretty serious galloping going on their tower, which is approximately the same height, just right next door to us. So these are conditions that were favorable to galloping on our tower back in February, and it just happens that we just got the snubbers in just in time. And here's a shot. The photographer got pretty brave and shot right up from the southeast guy anchor, or northeast guy anchor rather, at WHLA. You're seeing quite a bit of whip up the line and pretty seriously demonstrate.
Okay, anyway, I just tell you, I think we almost run out of time. So today we really give you a series of practical vibration engineering. Of course, I also show you about this kind of real vibration engineering. Of course, for this whole human body dynamics. Now we have a new kind of application in the virtual world. So that that is something as a new branch of our application. So that I do hope that you can really think about something unique, right, to see if you can try to make some interesting application about what we learned in our course, right, and some additional reference on our campus website. So that again, do you have any question? Any question? So that this is something again, our midterm exam coming next week. So that most likely, I will tell you that the content midterm exam will starting from the first lecture to today's lecture, and so that then so that you have time to prepare. So this is something I don't do any question. Of course, midterm exam usually will give you some of maybe some MC multiple choice, and then some brief question and some simple calculation. Okay, so that do you have any question about the midterm exam? Huh? Okay.